Alright, welcome to the review sheet for Chapter 10. This is for Chapter 10 that deals with, of course, the introduction to organic molecules and alkanes, but I can change this as simply from Chapter 10. Oops, Chapter 10. Okay, so we started off this chapter differentiating between organic and inorganic. The thing about organic compounds now is not that they come from organisms, or that they're natural or good or healthy or anything like that. Simply that they contain the element carbon. Inorganic compounds contain, well, not only do they contain some of the same elements that organic compounds contain, but the main thing that distinguishes them is that they contain non-metal elements. So again, if you remember your periodic table, draw a quick periodic table here. All right, so hydrogen is included in organic compounds. Helium not. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. If you look at your periodic table, there is, actually let's put here, below boron is aluminum, and we have silicon. There's a little staircase on your periodic table that separates the metals from the non-metals. And so really we're just talking about carbon, nitrogen, oxygen, the halogens, fluorine, chlorine, bromine, iodine, maybe sulfur and phosphorus, of course hydrogen, and that's it. In organic compounds, the intermolecular bonds, well, we can say they're weak. We didn't really talk about where these are bound. This is inter means between molecules. Okay, so we didn't really talk about how these intermolecular bonds arise between molecules in organic, but they're London dispersion forces, also called van der Waal forces. And they're the main thing about them is they're weak. For inorganic, they're strong, and these are ionic bonds. The intramolecular interactions, these are now within the molecule. For organic compounds, the intramolecular are strictly covalent bonds. There are really no molecules in inorganic. They're not molecular compounds. They are ionic. How do you spell ionic? That is not how you spell ionic. Ionic. But we'll put here ionic as well. And the main thing here is when you say if you were to heat up an inorganic compound like sodium chloride, eventually that solid sodium chloride, the same stuff you put on your French fries or popcorn or whatever, would melt. It would become molten, and you're boiling, or not boiling, but you're breaking the ionic bonds that hold the sodium ions and chloride ions together. In organic compounds, they exist as molecules, and so when you heat up an organic compound, you're breaking these weaker intermolecular bonds. You're not breaking the covalent bonds. The molecule stays intact, but you're breaking the weaker interaction between the molecules. So these are weak, these are strong, these are ionic, these are covalent, and because you're breaking, when you boil or melt something, the melting point or boiling point here, you're breaking those weaker interparticle, intermolecular interactions. These have low boiling points and melting points, whereas inorganic have higher or high boiling points and melting points. Solubility, organic compounds tend to be nonpolar. So they're insoluble in water, right? But they're nonpolar, so they will be soluble in nonpolar solvents, chiefly, or other organic compounds. Inorganic, they're ionic, so they're polar, and they are soluble in water. These are generalities, of course. We know of many ionic compounds that are not soluble in waters, or at least very minimally soluble. Something like limestone, which is calcium carbonate, is not soluble in water. Organic compounds will burn. They're flammable, so they burn. Flammable, yes. Inorganic compounds, no. They're non-flammable. Okay. We talked about a number of different chemical formulas. Let me scroll down here. Okay, so we talked about many different types of formulas. The chemical formula simply gives you the number and types of atoms. So say, for example, we could have C5H12, something like that. The structural formula tells us how the atoms are arranged. Tells us how the atoms are arranged. And there's three main types of structural formulas we talked about. Expanded structural formula, where every atom and every bond is shown. Shown is an S, shown. So for C5H12, 1, 2, 3, 4, 5, we would show every carbon and every hydrogen. This is pentane, which is beyond the scope of this question, but I'm just going to write here pentane. Okay. A condensed structural formula only shows the carbons. And what is attached to them. Okay, so if you look at pentane here, we've got a carbon on the end which has 3 hydrogens, so that's a CH3. And then that's followed by a carbon with 2 hydrogens, so that's a CH2. And then another CH2 and another CH2. So CH2, CH2, and on the end again we have a carbon with 3 hydrogens, so we have a CH3. We could also condense this a little bit more, and if you notice we have 3 CH2 units in a row, so we could write it as CH3 parentheses CH2. We're going to take that 3 times, and then another CH3. Okay. The skeletal formulas only show the carbon-carbon bonds. And heteroatoms. What's a heteroatom? These are atoms other than carbon and hydrogen. So atoms like the halogens, nitrogen, oxygen. Right. So if you look at this molecule, we've got 1, 2, 3, 4 carbon-carbon bonds. Let me highlight these in blue. Right. 1, 2, 3, 4. So the skeletal structure for pentane is, there's the first one. Now I'm going to put this on an angle so you can see that it's not just one long bond with these guys head to tail, but at each vertex or each corner, each kink here, we've got a carbon. We also have a carbon at each end. Right. This is this first line I drew here was a carbon-carbon bond, so there's got to be a carbon down at this end as well. So this is 1, 2, 3, 4, 5. Right? Looks like an M, right? But 1, 2, 3, 4, 5. Just so that we understand the importance of writing structural formulas and why C5H12 doesn't really tell us the whole story is because we could have a compound that again has 5 carbons, so 1, 2, 3, 4. I'm going to put a branch down here. Okay, this is no longer pentane. This is going to be 2-methyl-butane, and we'll talk more about naming later. But the thing about these are both C5H12, but they have different structures, the different shapes, different structural formulas, right? So they have different names. This guy is pentane, this is 2-methylbutane. They have different shapes, different names, different properties. What they do have in common is the same chemical formula, C5H12. Okay, now the names of the first 10 unbranched alkanes. We'll put here the number of carbons, 1, 2, 3, 4, 5. First is methane. This is the name. And the chemical formula is CH4. The next is ethane. I'm just going to give you, I'm not going to draw the whole structure, I'm just going to give you the chemical formula. C2H6. Propane. C3H8. Butane. Whoops, butane. That's a B, butane. C4H10. Pentane, we did. That was pentane. C5H12. H12. You notice they all end in ane. They have this ane ending. It's because they're all alkanes. In organic chemistry, the suffix or the ending for the name always tells you what class of compounds these belong to. They belong to alkanes. They end in ane. The next 5. So it would be the number of carbons is 6, 7, 8, 9, 10. 6 is hexane. 7 is heptane. 8 is octane. Nonane. Decane. Hexane, the chemical formula is C6H14, C7H16, C8H18, C9H20, and lastly decane C10H22. If you notice the number of carbons, starting with 4 here, go up 2 at a time. So the general formula that we have for an alkane is Cn, right, where N is this number of carbons, right, and the number of hydrogens is 2 times that number plus 2 more. So if we've got 1 carbon, right, 2 times 1 is 2 plus 2 is 4. If we've got 10 carbons, 10 carbons, 2 times 10 is 20, plus 2 more gives you 22. All right. Isomers, as I alluded to before, isomers, the thing that's the same isomer tells you there's something the same. The prefix iso means the same. Isomers have the same chemical formula. But different shapes. So the atoms are arranged differently, and this means they have different names and properties. So for example, we had pentane, 1, 2, 3, 4, 5. And then we had 2-methyl-butane. I'm going to draw it a little bit differently. This is 2-methyl-butane. these are both C5H12. They have the same chemical formula but different shapes. They have different boiling points and melting points. And of course different names. This guy sticking off the end here is a branch. So let me go ahead and draw the main chain. Why is this a butane? Well, the longest continuous chain is only 4 carbons. 1, 2, 3, 4. The thing sticking outside of the red box is a branch. If it's a 1-carbon branch, it's a methyl group. That would be a CH3. And ethyl would be a CH2. CH3, propyl, 3 carbons, CH2, CH2, CH3. Now with propyl, you notice I have this bond here. That would be what we stick onto the main chain, but this bond could either be on one of the end carbons, which are indistinguishable from one another, so it doesn't matter if I have this bond joining the main chain on the left or the right, those are the same, but I could also have it in the middle, and so we have this guy, and that is the isopropyl group. Butyl would be 4 carbons, CH3, CH2, 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 and there's the bond that would stick on the main chain. Isobutyl, don't worry about. It's an isomer of the butyl, just as isopropyl is an isomer of the propyl group. Notice these alkyl groups end in YL. Right? Just as alkanes end in ane, alkyl groups end in YL. Okay. So those first 10 unbranched, or what we call normal, this would be unbranched, alkanes, methane, ethane, propane, and on through decane, right? You can go from 1 carbon, right? We just put remember there's carbons at the corners and in each vertex here. So we've got 4 carbons there, that's a butane, right? 1, 2, 3, 4 carbons. You go from a carbon through a bond to a carbon, through a bond to a carbon, through a bond to a carbon, and you get to all the carbons. That would be normal. A branched, like this guy, we've got a carbon here, in the middle, here, and up here. This is a branched alkane because we can go from a carbon through a bond to a carbon, through a bond to a carbon. Now, we can't back up and get to this carbon. We can't just fly through space to get to it. So the longest continuous chain here is just these 3. So this is a propane. And we've got a 1-carbon branch sticking out. Right? So this guy here is a branch, and it would be a CH3. So this bugger is going to be 2-methyl propane. If you notice, these 2 guys are isomers. They're both C4H10. Right? But one we call a propane because it only has 3 carbons in the longest continuous chain, whereas butane has 4. This fella here, this is a cycloalkane. So cycloalkanes form these rings. Remember, carbon always forms 4 bonds, never more, never less. So I'm going to put a couple hydrogens here. So on each corner, we've got a hydrogen. There's 4 corners in a square. This is cyclobutane. And although it is, we call it butane, it is not an isomer of butane. This is just plain ordinary or normal butane. We'll put here an N for normal. N-butane is normal butane. It's C4H10. This is C4, but it's C4H8. If you notice, each carbon only has room for 2 more hydrogens. So if there's 4 carbons, there's going to be 2 times that number of hydrogens. 2 hydrogens per corner, so C4H8. Cyclobutane is not an isomer of butane. Why is that? Although they both have the word butane in them, this has a different chemical formula, different number and types of atoms, and therefore they are not isomers. In order to be isomers, they must have the same chemical formula. So N-butane and 2-methylpropane are isomers, same chemical formula. Cyclobutane is unrelated. Right. The rules here for assigning these IUPAC again stands for the International Union of Pure and Applied Chemistry. So the first thing you got to do is find the longest continuous chain. Continuous chain of carbons. And this gives you the parent chain or the parent alkane. Right? So here we had 3 carbons in the longest chain. 3 is propane, methane, ethane, propane. Propane is the third one. Number the chain now starting at the end closest to the branch or substituent. It could be, instead of a methyl group, it could be, I don't know, we'll put a bromine on here. Start at the end of the chain, starting at the end closest to the branch, closest to the substituent. So starting closest to the branch. Also, these guys are called substituents. So in this case, we've got how many carbons here? 1, 2, 3, 4, 5, 6. Right? That tells us this is a hexane. And we're going to start at the end closest to the branch. So we're going to start here 1, 2, 3. In carbon 3, we have a bromine. So it's 3 bromohexane. Right? We would not start at the left side where it would be 1, 2, 3, 4 carbons before we get there. So start then closest to the branch. Identify, locate by number the branches or substituents, and string the name together. Remember, numbers are separated from, I'll do it this way. I'm going to have to write in 2 lines here. Numbers are separated from letters by a dash or hyphen. Oops. Dash. So if you notice here, it was 3 dash bromohexane. And from other numbers by commas. So remember, you can have more than one type of branch, and you can have more than one of the same branch. So let's have, let's make it a cyclohexane. Draw a cyclohexane here, and we'll put, say, a bromine here and a chlorine here. Now these guys are right next to each other, so the shortest path is simply going to be 1, 2. Actually, let's do it this way. We'll put 2 chloros here. Right? Now bromine comes before chlorine in the alphabet. So the last thing it says, put branches in, I'm just going to write ABC order for alphabetical order. So this bugger here, we have a cyclohexane ring, so that's the parent alkane, cyclohexane. And we have a bromine in carbon 1, so it's going to be 1 bromo. Right, separate numbers from letters with a dash. And then 2,2-dichloro. Got to run out of room, just kind of squeeze it in there. 2,2-dichloro. Separate numbers from each other with a comma. And if there's 2 of the same branch, we say di. So multiple branches at the same time are given the prefixes. 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa. But tetra is probably enough. So 2,2-dichloro means both of these chloros are on the same carbon, carbon number 2. Okay, as I said earlier, if they are isomers, they have the same chemical formula, but different, it says down here, but different names, shapes or structures, and properties. Do not confuse different conformations with different structures. These are the same compound, they're just drawn slightly differently. If do a little practice naming here now, find the longest continuous chain. Right? If you name 2 compounds and they follow the rules correctly, you end up with the same name. They are the same structure. So starting at closest to the branch, this is carbon 1, 2, 3 on carbon, well, actually, how many carbons in the longest continuous chain first? 1, 2, 3, 4, 5, 6. So this is a hexane. Right. On carbon 3, we have a branch, so this is a 1 carbon branch, should be 3 methyl hexane. Now this next one here, right, just because I number this left to right doesn't mean I have to number this left to right. The numbering is always starting at the end closest to the branch. So here I'm going to number right to left, 1, 2, 3. And again, this is 3-methylhexane. These are not isomers. These are the same compound, just drawn slightly differently. Another type of isomer, well, actually, let me go back. The isomer, let me do it here. Find a little bit of room here. The isomers we've been talking about before, they come in 2 main classes. They have what we call constitutional isomers, and then stereo or geometric isomers. So stereo isomers, sometimes these are also called geometric isomers, or simply cis-trans isomers. Let me give you an example of constitutional isomers. Let me draw. This is going to be a cyclohexane. I'm going to draw it slightly differently than what you saw before. We're going to kind of draw it edge on. So this edge that I'm made a little bit thicker here is kind of coming out of the screen at us. Okay, so I'll draw another one here. Didn't do quite as good of a job, but anyway, put a couple guys in here. We'll have a bromine here, and then maybe a bromine here, and then we'll put a bromine down here, and a bromine here. All right, now these are constitutional isomers because the numbering is different. If you notice, these two guys are right next to each other. This is one bond, there's a carbon. If we were to blue here, we've got a carbon, carbon, carbon. These are cyclohexanes, right? There's a bond like that. These dots are the carbons. So there's 6 carbons in a ring, so these are cyclohexanes. And this molecule here, this is 1,2-dibromo cyclohexane. This compound on the left, these bromines are not on adjacent carbons. It's 1, 2, 3, 4. If we go around the backside clockwise, if we go around the front counterclockwise, 1, 2, 3, 4, it's still 1, 4. So this is still a dibromo, but it's 1, 4 dibromo cyclohexane. Cyclohexane. So you see the numbers are different, the order of atoms are different. That's the thing about constitutional isomers. That's the kind of thing we've seen before. Geometric is a little bit different. Geometric, I'm going to redraw this 1,2-dibromo cyclohexane again. But the thing about cyclocompounds is once you form a ring, the molecule loses this rotational freedom it has about carbon-carbon single bonds. And if you remember when we were talking about finding the longest continuous chain and how you can go around corners, those molecules can kind of kink up and twist and whatnot, and that's based upon this rotation about carbon-carbon single bonds. But when you put them in a ring structure like that, they lose that rotational freedom, and you end up with a rigid or fixed ring that can maybe kind of bend and pucker and twist a little bit. But you can have these bromines on the same side in which they're cis. So this would be the cis 1,2-dibromo cyclohexane, blah, blah, blah. Trans is when they are on opposite sides. So trans here just for kicks, I'm going to put them in slightly different. This is still 1,2 because they're in adjacent carbons, 1,2 dibromo, but one's on the top and one's on the bottom. Hopefully that's obvious to you, but if not, I'll put the hydrogens in here. Right? So one's on the top side, one's on the bottom side. This is trans 1,2 dibromo. Notice there's still 1,2, so the order is the same. Dibromo, cyclohexane, ... But so trans means opposite sides. And cis is the same side. And these are geometric or stereoisomers, or if you wish, cis-trans isomers. We will have some other types of stereoisomers later, but in the first few chapters here in organic, we're just going to talk about cis-trans isomers. All right. Alkane combustion reactions. You should recognize that if you combine one of these hydrocarbons, I didn't use that term before, but hydrocarbon. One thing about hydrocarbons, they make good fuels. Octane, if you noticed, was one of the unbranched alkanes. We need you to know how to count the 10 in organic chemistry. 8 is octane, and that's what you put in your gas tank of your automobile. These hydrocarbons contain only hydrogen and carbon, and so when you burn them, you get carbon dioxide and water. Carbon dioxide is this greenhouse gas that everyone's worried about. And burning fossil fuels, I didn't mention fossil fuels, but fossil fuels are fuels that come from long time ago dead things, like fossils. Fossils are long time ago dead things, plants and animals, and so these, what would it be? Oil, coal, natural gas contain hydrocarbons. These are fossil fuels because they're dig them out of the ground from long ago dead stuff, and we can burn them and get energy from them. So we didn't put this here. We can say plus energy, light and heat energy. One of the problems is we create carbon dioxide among other pollutants. If you're burning coal, one of the major pollutants is mercury. If you burn oil and natural gas, actually if you burn anything, you're going to produce nitrogen dioxides, which create smog. Coal also produces sulfuric acid, which is a component of acid rain, so it damages soils and plant life. Anyway, carbon dioxide has been in the news a lot because it's a greenhouse gas, and this leads to global warming. So people talk about their carbon footprint and essentially how much energy they are using and how much carbon dioxide they release in the atmosphere to produce that energy, and how much they are destroying the planet that we live on. Okay. All right. Lastly, the key physical properties of alkanes and how chain length affects these properties. Okay. An increase in chain length increases the boiling point and melting point. And they say increased chain length. Increased, you can read this as number of carbons. Okay. So for example, butane, C4H10, its boiling point is 0 degrees Celsius, about 32 Fahrenheit, whereas hexane, C6H14, hexane, I believe, is about, I'm going to say about 20. I'm not exactly sure, right? But it's got more carbons, right? So we'd expect its boiling point to be higher, so it increases the boiling point and melting point. Lastly, alkanes are insoluble in water. We talked about that at the very beginning. And they are less dense than water, and they burn. So picture, if you will, an oil slick that's on fire. It tells you that the hydrocarbons in that oil do not mix with water. They're insoluble in water. Another term for that is immiscible. We'll use that word, immiscible. They do not mix with water. They float on top of the water, so they're less dense, and of course they burn. They're flammable. Alright, so that's the end of this. We'll have another review sheet for the Alkanes, Chapter 11, coming up.